Professor Doney back. We're continuing our discussion about waves and vibration, simple harmonic motion. We just talked about springs and pendulums, and now we're going to talk about waves on a string. Now, the wave equation that we have that applies for all waves is the velocity, if we know the velocity of the wave in the medium, or non-medium if it's electromagnetic, is equal to wavelength times the frequency. Now, if we're in air, sound waves, we're talking about 343 over here, plus or minus depending on temperature. But if we're talking about being on a string or in a membrane, the velocity is going to depend on the tension and m over L, which is known as the mass per unit length. Sometimes we use mu as that. And that's the linear mass density of the string, how heavy the string is per unit length or per meter. So if we're on a string, we have to use that equation, but this one still applies here. All right, so let's just do an example here. Pull up another color. And our example is we're going to have a string that's 10 meters long, and we weigh that 10 meters or put it on the scale and find out it equals 0.0001 kilogram. All right, just from fairly easy numbers. And you could do that, 10 meters, 1 kilogram. Actually, just make it 5, just so we have some different numbers in ones. And what we're going to do is take that string and we're going to tie it off against the wall and then have it go over a pulley on the other end, and we'll have a mass hanging on that end, and that's going to put some tension under or over that string. Okay, let's make the length of this 1 meter, and we hang the mass on there and we pluck the string and we end up seeing that it vibrates. Okay, now understand, when we have it fixed between 2 points, the vibration of that is going to cause sort of the up and down, the standing wave of essentially a half a wavelength. It doesn't give us a full wavelength. Remember, a full wavelength goes up, comes down, and comes back up or starts over. This is only giving us this part of it. Okay, so that's a half a wavelength long. So if you're asked what is the wavelength of the wave on that string at its resonant frequency, we would have to just say, well, the wavelength equals, well, twice that distance, which is 1 meter, so it makes it 2 meters. Okay, so let's find, we want to find some frequency going on here. So if we want to find frequency, we have to go back to this equation, the wave equation, and frequency is going to equal velocity divided by wavelength. Now, we already have the wavelength, which is 2 meters. We have to find velocity. Where does velocity come from? Well, it's going to come from this velocity equation with tension net. So if we say the mass is 2 kilograms, we're going to say the velocity is square root of force of tension. Force of tension, again, is up from Physics 1. It equals mg down, so that's going to be the mass, which is 2 times 9.8 on the top. M over L is going to be the m over 10, so that's 0.005 over 10, and that's going to come up with some number of newtons, somewhere around the square root of, what is that, 9.8 times 2 divided by 0.005 times 10. I lost it. Well, it'll come up with a number we'll grab there. You can easily run that in the equation. Just be careful when you do this part underneath here. Alright, once we have that velocity, what I can do is kick it back up here into our wave equation, and I'll have that tension divided by meters, and that is going to give us the frequency of the wave that is there. Okay, now a couple comments while we're here talking about this. Understand that if we increase the tension by hanging a larger mass here, the result is the velocity is going to get tighter, so the velocity is going to be faster. If the velocity is faster, the result is the frequency goes up.